In this tutorial, we're going to learn about calculating correlation in data. And the example that we're going to use actually comes from a public data set. All of the data that you see in today's exercises are available through the World Bank's website. You can also access these data through Google and Google's Public Data Explorer, which allows you to make a bunch of charts and graphs and all of those things. But if you want access to the raw data, go to the World Bank's website. For this lab exercise, I've compiled a dataset for you called worldbank.dta. Go ahead and open that dataset up on your computer. Now what this dataset contains is, it contains public data from the World Bank where we can examine trends on immunization coverage for measles and for DPT vaccines over time, and I've restricted this dataset to low-income countries. So what we're looking at is temporal trends in low-income countries for immunization. The first thing we want to do is calculate a pairwise correlation between measles vaccination coverage, DPT vaccination coverage, and time. The command that we're going to use in Stata is pwcorr, P-W-C-O-R-R. Alternatively, you could use the drop-down menu to do this analysis. To find this through the drop-down menu, we go Summaries, Tables, and Tests, Summary and Descriptive Statistics, and then click on Pairwise Correlations. We're interested in pairwise correlations for all variables in our data set, so we can just leave variables empty if we're interested in all variables, and we can hit Submit. So this gives us a matrix of correlations. We see that the correlation on the diagonal is always 1 because what this calculates is the correlation between year and year. So it's just there for show, but really this isn't giving you any information. The diagonal is always going to be 1. Now we are interested in the correlation between DPT vaccination and year. That's going to be equal to 0.9476. Going down one further, we can see the correlation between year and measles is 0.9387. And again, we can look and see the correlation between measles and DPT vaccination is 0.9973. So those are the Pearson correlation coefficients calculated using the pwcorr command. Alternatively, we could have used the correlations and covariances option available in the drop-down menu, and we get basically the exact same output. So these both calculate for you the Pearson correlation coefficients. The next thing we want to do is we want to make a scatter plot including both measles and immunization coverage on the plot and track those as a function of time. And we're going to try to use this scatter plot to explain the results, these high Pearson correlation coefficients that we saw above. To make a scatter plot, we go Graphics, Two-Way Graph. On our scatter plot, we want to include basically two different plots. We want one plot for time versus measles vaccination and one line for time versus DPT vaccination. So we're going to create two different plots here. The first one, create, we want to scatter plot. Our Y variable will be measles. X variable is going to be year. We want to sort on the X variable and hit Accept. Now we want to create another plot, so hit Create again. Now my Y variable is DPT, my X variable is year. Again, sort on the X variable, hit Accept. And now once we define those two plots, we hit Submit. So examining this scatter plot, we see first of all that there does appear to be a strong positive relationship between time and immunization coverage. Further, when we look at measles, which is in blue, and DPT, which is in red, we see that basically they track very closely together. These trends are very similar, so it seems like whatever efforts were made to scale up immunization coverage, it seems like they happened pretty much so in parallel for both of these two vaccinations. Consequently, the fact that we see this strong positive trend with time explains the positive correlation coefficient we saw between vaccination and time, and we saw an even higher correlation coefficient for measles and DPT immunization coverage, and that is due to the fact that these guys really do track with basically exactly the same pattern. So we would expect to see a correlation coefficient pretty close to 1. And so again, reviewing what we saw before, that's exactly what we saw, correlation close to 1. and strong positive relationship with time. Next, we want to test whether there's a linear relationship between time and measles vaccination coverage. In this setting, what's our null and alternative hypothesis going to be? Remember that the Pearson correlation coefficient is a measure of the strength of the linear relationship between two variables. So what we're going to do is we're going to test the null hypothesis that rho is equal to 0, our correlation coefficient, against the alternative that rho is not equal to 0, and this is going to be a test testing the null hypothesis that there's no linear relationship versus the alternative that there is some linear relationship between measles and time. To do this test in Stata, all we really need to do is use that pwcore command again, but we need to specify one additional option. So I'm interested in the correlation between year and measles. And then I go down and I want to print the significance level for each entry. And hit submit. So now when I run the pwcore command, I add this additional sig option. And what that does is it gives me the correlation coefficient in this top line. And on the bottom line, that gives me a p-value. So what I can say here is that my p-value is very small. It's less than 0.001. So in this case, I would reject my null hypothesis, include that there is a positive relationship between time and measles vaccination coverage. Recall in class, though, that we learned that there's also a non-parametric correlation estimate. We can use the Spearmans correlation coefficient. So if you're interested in calculating the Spearman correlation coefficient, you can use the Spearman command in Stata. Spearman's rank correlation via the drop-down menu, you go Summaries, Tables, and Tests, Non-Parametric Tests of Hypotheses, and then click on Spearman's rank correlation. Now the variables we're interested in, again, are year and measles. So now, before, remember, we tested whether there was a linear relationship between measles, immunization coverage, and year. Now we want to transition and we want to do, instead of looking for a linear relationship, we're going to look for a monotonic relationship between those two variables. So if we're using Spearman's rank correlation coefficient, what we can do is we can test that rho s is equal to 0, test the alternative that it's not equal to 0. And essentially what this does is, instead of linearity, we're now testing the null hypothesis that there is no monotonic relationship between time and immunization coverage versus the alternative that there is some monotonic relationship between time and measles vaccination coverage. So to do this in Stata, we just run this Spearman command. It tells us that we're using 29 observations. The estimated value of Spearman's rho is going to be equal to 0.9695. And then we go down here and we test H0, that year and measles are independent. There's no monotonic relationship between year and measles. And that gives us, again, a p-value that is less than 0.001. So regardless of whether we use the Pearson's correlation coefficient or the Spearman's rank correlation coefficient, we conclude that there is a positive relationship between year and measles immunization coverage. And again, examining the scatter plot that we saw and looking at this correlation matrix that we calculated, we end up with really high correlations in this example. Now, thinking about your standard public health applications, would you always expect correlation coefficients that are this large, or are these exceptionally high correlation coefficients? So this is an interesting question, and I think in this example, we see a very, very clear pattern in the data. It's very clear that immunization efforts have been scaled up and they've been increasing over the past 30 years within low-income countries. Now, this may not be true within individual countries. It may not be true within specific locations within individual countries. But the point here is that by aggregating, we end up with these really smooth trends over time that give us a really big picture of what's going on. However, when you think about public health applications, typically what you're doing is you're collecting and analyzing data at, say, the individual level. Usually maybe you're going to go interview a person, etc. And when you're dealing with individual level data, there's a lot more factors that, for instance, impact whether an individual gets immunized. Therefore, if we were looking at individual level data in this example, we'd see a lot more variability within individuals. And therefore, when you're dealing with individual level data, you tend to see much lower correlation coefficients. I think one of the really neat things about using this World Bank data is the fact that by dealing with these aggregated measures, by aggregating over all low-income countries, we average over all of that individual level heterogeneity, and we obtain these very clear pictures of large-scale trends that are very consistent over time and lead to very large correlation coefficients that give us a clear picture of what has been going on over time at a very broad scale. I would encourage you to visit the World Bank site, click on their Data tab, and go and explore some indicators for your own country or for a region of the world that you're interested in looking at.